In the current chapter, we are going to understand about the basics of the flow cytometry and the basics, particularly those concerns its application in the field of hematology. The first question which comes in our mind that what exactly flow cytometry is, and the answer to this question lies within the name itself. We can see this flow cytometry name has got two components. One is flow and second is cyto. What do we mean by cyto? Cyto means the cell. So flow cytometry is first of all the study of cell. And when we talk about in hematology, what are those cells? They can be any cells which are present within your peripheral blood or the bone marrow, or hematopoietic cells derived from elsewhere, something like lymph nodes, or maybe the lymphoma deposits in your tissues, or maybe the lymphoma cells which are present within your fluids, something like CSF, pleural fluid, or even the ascitic fluid. So those are the cells that we study constitute the cytoterm. Now what is flow? Flow means that we are going to study these cells while they are flowing in a fluid phase. Let's understand them better with the help of this example. So let's say this is a cell from our peripheral blood, maybe like a lymphocyte, and now this cell is flowing in the fluid phase in a single file. Single file means that at one time only one cell moves within the fluid. Okay. Now while its motion within this fluid phase, at a particular section or a particular area, we are going to bombard this cell with the help of a laser. And as soon as a laser light will fall on it, we shall be able to understand some properties of this cell with the help of this laser light. Broadly, these properties you can divide them as scatter properties and the fluorescence property. Now, starting about the scatter properties first. The important thing that needs to be remembered about the scatter properties is that these properties are present within the cell itself. You don't need to label the cell with any type of special reagent to study them, and they are produced as soon as the laser light falls on them. They can be further divided into forward scatter and side scatter. The second property that we study is fluorescence. Now fluorescence can be inherent to the cell, and to be more specific, most of the time it is when we give it to the cell. How is the fluorescence property studied? I shall be dealing in the chapter in its due time. Now let's start with scatter properties, and starting with forward scatter first. Let's study them in greater details one by one. Coming on to the forward scatter. Now let's say this is a laser light source and this is falling on this screen. This screen is actually a recording screen which can measure how much is the amount of light falling on it and how far it is falling, where exactly this light is falling. So let's say when there is no cell which is obstructing the path of this light will go and fall at this point, and this will be the origin. And actually this screen is not in form of a single line. It's actually not in one dimension. It's a two-dimensional structure and actually in form of a square. And when you see it from behind, how this light will appear, it will appear like a single small dot at the center. While if you see, there's going to be no light at any of these points when there is no particle or no cell obstructing the path of this light. Whole of this area is going to be free of any amount of light from this laser. Alright. Now let's say we introduce a cell in path of this light. What will be the result? As a result of this cell obstructing the path, the light will now bend along the edges of this cell, and instead of falling at this center, the origin, it's going to fall at a point which is away from the center. And this distance from the center is called as forward scatter height. Okay. Now let's say I introduce a bigger circle in the path of this light. What will be the result? There will be more bending of the light, and now the light will fall at a point which is even more further than the previous one. So the forward scatter height is going to be more for this cell as compared to the previous one. So what do we understand by this? we understand by this is that forward scatter is primarily determined by the size of the cell. Okay, this thing we have understood, that forward scatter is primarily determined by the size of the cell. Now let's see this forward scatter on some different dimension in two dimension. So initially you have seen that the light was falling at the center and there was no light anywhere else on this recording screen. But when a cell is introduced into its path, the light is going to fall at a further place where actually there was no light earlier. And this will be seen in two dimension in form of a shadow at the center and some amount of light falling along the edges of this shadow. Now this will appear in form of a circle when a single cell is flowing or obstructing the path of the light at one time point. The area of this circle, this area is going to be equal to pi r square, and r in the current setting is equal to forward scatter height. So area and height are going to be correlated to each other by this formula, where area is going to be proportional to the square of the height. Now let's plot this area and height along a xy graph, where area is being taken on x-axis and height is being taken on y-axis. Now can you recall from your 11th standard physics what will be the graph, how the graph will look like when the component on x-axis is proportional to the square of the y-axis? We know that it's going to form a parabolic curve like this, and all the cells which are flowing in a fluid phase in a single file are going to fall on this parabolic curve. The cells which are going to be which will fall here are going to have both higher forward scatter area and higher forward scatter height. That means these are going to be the larger cells, and the cells which fall more close to the origin are actually the smaller cells. And this is how a real life graph will look like. So you see these all gray dots, these are the cells which are flowing in a single file and are falling along this parabolic curve. However, you can also see there are some cells which are not following this parabolic curve. These are what we called as doublets. And what are doublets? Doublets are the cells which are not flowing in a single file. They are 2 cells, 3 cells, or maybe more cells stuck to each other and flowing in a group. Now we don't want to study these cells. As soon as we start analyzing any case of in flow cytometry, first thing that we do is that we exclude the doublets. And why do we exclude these doublets is, let's say for an example, a B cell and T cell are sticking to each other and we are trying to study the fluorescence pattern in them. How that fluorescence pattern is studied, I'm going to come into the next slide, maybe next to next slide. Now let's say the B and T cell are sticking to each other, and when you analyze this cell will be giving you both B type of signal and T type of signal, and we don't want that thing. That may cause confusion in understanding the immunophenotype of the cell, which is our primary objective. Okay, we don't want to study the doublets, and that's why the first step is the exclusion of these doublets. And how do we exclude these doublets? Is by plotting forward scatter area and height plot and choosing only those cells for analysis which are following in this parabolic curve. This is about the forward scatter. So the forward scatter is primarily determined by the size of the cell, and the singlets forward scatter area and height plot, they will lie along a parabolic curve. Now let's see what is this side scatter business all about. We have seen that forward scatter was due to the bending of the light along the edges of the cell and was primarily determined by the size of the cell. However, we see that there is some reflection of the light. It's not deflection, say as in case of forward scatter. It's actually the reflection of the light by the constituents of the cytoplasm of the cell along a 90-degree angle, which can be detected with the help of this detector. And what are the primary determinants of this scatter, side scatter? There are two important determinants of this scatter or this reflection. First is the granules. The cells which are going to have higher number of granules are going to have higher side scatter, because these granules acts like a mirror, and the cells which are going to have higher number of granules will be having higher side scatter. So what are the cells which that you know of contains granules in hematology? I hope you're talking about the myeloid cells. Both the mature neutrophils and its precursors like myelocyte, metamyelocytes are going to have higher side scatter because they contain a lot of primary as well as the secondary granules. And which are the cells which are the cells that will have the least amount of side scatter? Of course, I know that you are thinking of the lymphocytes, because usually they are devoid of any type of granules. What about monocyte? Now monocytes, remember, also have got some amount of lilac color granules in their cytoplasm. So they will show a side scatter which is higher than that of a lymphocyte. But since the number of granules are very low, they will have side scatter which is less as compared to the mature neutrophils or the myeloid cells. And lymphoid cells, obviously, because they do not have any granules, are going to have the least amount of the side scatter. Now the second important determinant of side scatter is the presence of vacuoles. These vacuoles actually acts like a mirror, something which is called as total internal reflection. You must have heard of that phenomena in your 11th standard physics, where we know light bends when it travels from a higher density media to a lower density media, something like a vacuole, and these vacuole, by the same phenomena of total internal reflection, are going to reflect the light along a 90-degree angle. Now let's remember from our morphology what are the cells that contains vacuoles. Of course, the first answer that comes in our mind are the Burkitt lymphoma cells. Actually, the vacuolization is a feature which is most commonly seen in two cells. One is the B cell and second is the monocytic cell. So the most important differential diagnosis when you're seeing vacuolization is, one is Burkitt. We know that Burkitt cells are the large cells or large to intermediate size cells which have got deep basophilic cytoplasm studded with a lot of vacuolization, and because of those vacuoles, these cells are going to have higher amount of side scatter as compared to the normal mature lymphocytes. The second cells, as I have told, are going to be the monocyte and the monocytic precursors, the monoblast. Because of the vacuolization, they will show you higher amount of side scatter. So to summarize, forward scatter is primarily the size, while the side scatter is primarily the granules and the vacuoles. All right. After this scatter, let's come on to what is the fluorescence. Now to understand the fluorescence, let's say we have this antibody. Let's say this is a CD20 antibody. Now we know that CD20 is an antibody which goes and binds to the CD20 antigen. And which are the cells which contain CD20 antigen? Of course, the B cells. Almost all the mature B cells except plasma cell will contain a lot of CD20 antigen on their surface. Okay. Now let's label this, or let's tag this antibody with a fluorochrome. Now let's see what is a fluorochrome. Fluorochrome, we again remember from our 11th standard physics, are some particles which, when excited by a specific wavelength of light, they get excited, and when they fall back to their native state, they emit some light in return, and that light can be detected with the help of detector. Now we have labeled this CD20 antibody with the help of a fluorochrome. Let's say this is a FITC fluorochrome. And now we react this labeled antibodies with your peripheral blood. Now which cells do you expect will get labeled by this antibody? We know only the cells which are of B cell origin will get labeled by this fluorochrome. And when a light signal will fall on this B cell will detect the presence. This B cell will give a signal because of the presence of this FITC fluorochrome on its surface, bound with the help of this CD20 antibody. So now let's say a random cell. We don't know which cell it is, and when light is falling on it from a green laser. We know that FITC fluorochrome gets excited by the green laser. So as soon as the green laser light falls on this cell, you don't detect a FITC signal. What do you understand? You don't detect a FITC signal means there is no FITC FITC fluorochrome attached to it, which means there is no anti-CD20 antibody attached to it, which means it doesn't have CD20 antigen, and that in turns mean it can be anything but not a B cell. It may be a T cell, it may be a NK cell, it may be a monocyte, or it may be a neutrophil, or anything but not a B cell, or not a mature B cell to be specific. And vice versa, if you get a FITC signal, you can say that this is a cell which contains a CD20 antigen on in its surface and likely is of B cell origin. Now this is something like immunohistochemistry, where you also label the cells with the help of an antibody and study if it is present or not with the help of some enzymes. But the advantage of flow cytometry is that at one given time point, you can label the cells with more than one type of antibody. And now let's say in addition to this CD20 antibody, we have also added to the same sample an antibody which is CD3 antibody, and have labeled this antibody with a different fluorochrome which is PE. Now the light emission of this PE is going to be different from the light emitted by this FITC, and we can differentiate on the basis of the type of light which is being emitted, that whether it is a CD3 or whether it is a CD3 and a cell, positive cell, or whether it's a CD20 positive cell. And similarly, in the same sample, you can add more number of antibodies, let's say CD56 antibody, to label NK cells, but should be labeled with the fluorochrome which has got an emission or the emitted light different from FITC and different from PE, so that we can separate that from which type of antibody that signal is coming from. For an example, in my lab, I am using a BD Fax Lyric flow cytometer. This flow cytometer has got 3 different lasers to excite 12 different fluorochromes. Like within the green laser, the activation of FITC, PE, PE size 7 and PERCP takes place, while red laser excite APC, APCH7 and APCR700 fluorochromes, while violet laser in turn activates 5 different fluorochromes which are BV421, B510, B605, BV711 and BV786. What do we mean by these 12 different fluorochromes? That means at one given time point, I can study presence or absence of 12 different antigens on one particular cell. That is the advantage over the immunohistochemistry, where you can study only presence or absence of one antigen. While see, we are multiplexing it. This is what is called as multiplexing, where we are going to study almost like 12 antigens at one time point. Now there are flow cytometers which are coming up with 26 fluorochrome reading capacity. However, those flow cytometers are more difficult to operate. Right now we are using a 12 color flow cytometer. Now let's understand what is that overall input and what is the overall output. So let's say this is a cell. First laser hits this cell, and this cell helps us to understand the forward scatter and the side scatter. The forward scatter will help us about understanding about the size of the cell. Side scatter will tell whether it is granular or not. The second thing is, now this cell is again hit by a red laser, a green laser and a violet laser, and in turn these 3 lasers, green, red and violet, are going to activate 12 different fluorochromes and will help us understand the presence or absence of 12 different antigens on these cells. And all these things are happening simultaneously on each and every cell which is passing through this cross section. Okay, so this is the advantage. This is the multiplexing, which is the most helpful thing or the most advanced thing over the immunohistochemistry. With this, we come to an end of this chapter, and actually this is how a forward scatter and a side scatter plot looks like, and how further we divide these cells and understand the sublineages, understand, separate out the population will be a topic which we are going to study in details in our next chapter. So guys, stay tuned and subscribe to the channel. We shall be adding more and more number of cases and more basics about the flow cytometer. How do you process the sample? How do you analyze the cases? Important cases I'm going to discuss with you. And later on, I'm also going to discuss the difficult one or the complex cases as well. With that, I take your leave, and that will be the end to it. Thank you. So coming up next is gating and population separation in the next chapter. Thank you.